Hello again everyone, welcome back to ptet.chemistry channel. So in this tutorial, I'll go through this A-Level 9701. It's a June 2021. It's a paper 2-1, a fairly recent paper. Regardless, it assesses everything that Cambridge has already told you will be coming out a couple of years in advance. So you should always check your specification and your syllabus. Anyway, before I start my tutorial, so there's a button on the bottom right of all the tutorial videos on YouTube channel. So make sure you click the button on the bottom right to subscribe to the channel. If you like these videos, leave a like or comment on the videos on what else you would like to see in the videos in the future. However, I am already trying my best to accommodate all these restructured format after Cambridge sent me an email talking about copyright violations of their question paper. So please don't ask me to show the question paper again, alright? Because I will not jeopardize my own center as well as my own students at the expense of this YouTube channel, which I do in my free time, unfunded, and also yeah, I just do it in my free time out of goodwill and also out of interest of sharing my chemistry knowledge with you all. Alright, so don't forget to follow me at ptet.chemistry. That is at ptet.chemistry on Instagram, Facebook, and Twitter to get connected and to send in questions, messages, and whatnot. Let's get started. In this first question, we have ethane dioic acid. And they first start off by asking us to define something, which is relative molecular mass. Relative molecular mass is something that we are very familiar about in terms of MR this and MR that. Relative molecular mass is simply defined as the average mass. So the key term there really is you have to talk about average, because there were 4 definitions in the first line of the syllabus in A-Level chemistry for 9701. There's relative isotopic mass, which you can never have average for relative isotopic mass, but the remaining relative atomic, relative molecular, as well as relative formular mass is all about average mass. For molecular mass, is the average mass of one molecule, and this is a relative mass, so it is relative to the mass of 1/12. Actually, is relative to 1/12 of the mass, relative to 1/12 of the mass of n atom, meaning one atom. If you don't like n, you can use the term 1 atom of carbon-12 isotope. Some people don't like carbon-12 written like that. You can write as carbon-12. This is the same thing as saying carbon-12 isotope. So that is just basic definition there. Next up, state the empirical formula. So empirical formula is defined as the simplest whole number ratio of atoms. So what we have here is ethane dioic acid. You will know I'm a big fan of drawing skeletal formula. The structural formula is as given. So HO2C and CO2H. Total up the number of carbon, which is 2. Total up the number of hydrogen, which is 2. Total up the number of oxygen, which is 4. That is what you call molecular formula, because it shows the actual number of atoms in one single molecule. So what you have is you divide by 2 throughout, and you get, oops, I don't mean to do that, and you get 2 divided by 2 will give you 1. 2 divided by 2 will give you 1. 4 divided by 2 will give you 2. So it's CH2O for the empirical formula, and that is what you want for this particular question. Okay. Part 3, how many atoms of carbon are present in 0.18 gram of ethane dioic acid? The first thing we will do is find out the MR. And since we have already worked out the molecular formula like this, we might as well just use it, because it's a lot easier to just count individual of carbon, hydrogen, and oxygen. So 12.0 from the periodic table times 2, because you have 2 carbon plus 2 times 1.0. plus 16.0 times 4. Your calculator show you 90, but you know better to actually write as 90.0 as per the accuracy given in your periodic table for the sum of the relative atomic masses. So what we have is, we first find out the mole first. So the mole is going to be mass over MR, and that will give me 0.18 gram divided by 90.0. And my calculator show me 2 times 10 to the minus 3 mole. And I know how to relate the number of moles with the number of atoms, because 1 mole of C2H2O4 has 2 mole of carbon atoms. You need to be very careful here. So therefore, 2 times 10 to the minus 3 mole of C2H2O4 has 2 times 10 to the minus 3. And that will give me 4 times 10 to the minus 3 mole of carbon atoms. Now after working out that much carbon atoms in terms of mole, so the number of carbon atoms is going to be Avogadro constant multiplied by 4 times 10 to the minus 3. Avogadro constant is stated in your data booklet as 6.02 times 10 to the 23. So multiply that by 4 times 10 to the minus 3. My calculator show me 2.408 times 10 to the 21 atoms. But looking at the data given, it was 0.18, so it was one significant figure and two significant figure. I think it is appropriate for me to write down my final answer to two significant figure based on the 0.18 gram, which was two significant figure. So that should be my final answer there. Okay. So on to part B. So this is question 1, part B. We have solid ethane dioic acid reacts with aqueous calcium ion. So we have ethane dioic acid, which is a solid, and then you react with calcium 2 plus aqueous. What you're going to get is going to get a precipitate of this calcium ethane dioate. So there's O2, well, O minus and minus, so it's minus 2 overall, and that will be balanced out by calcium 2 plus overall. This is calcium ethane dioate. Ethane dioate means it's a dioate ion, okay, because it's a dianion with a calcium 2 plus, the charge balance out. Now this calcium, well, this is a solid, and of course then you will kick out 2H plus like that, so obviously the 2H plus goes off and you have to balance the equation because it's plus 1 times 2, so plus 2 there. Anyway, so balancing equation is not what they want here. Part 1 is actually asking you what happened when calcium ethane dioic acid is heated, and they want you to include state symbols. So this is a solid, and when you heat it, so delta there refers to heat. If you don't want delta, you can put down heat. You're going to get calcium oxide, you're going to get carbon dioxide, and you're going to get carbon monoxide. So 1 calcium give you 1 calcium, 2 carbon, 1 carbon and 1 carbon there, and 1 oxygen plus 2 oxygen is 3, plus another one is 4. That's how you get the 4 oxygen. Calcium oxide is a giant ionic structure. It has a giant ionic lattice structure. So it's got a metal and non-metal consisting of strong ionic bond, high melting and boiling point, solid at room temperature and pressure. Carbon dioxide and carbon monoxide are simple covalent molecule in the presence of heat, which you have used to decompose and to break down this thing. In the presence of heat, you're going to produce these as gases. State symbols are required for you to score 1 of the marks, and of course whatever equation you write has to be balanced. Part 2, identify the type of reactions. I've just told you that these are decomposition. These are decomposition in the presence of heat. That is why we call it thermal decomposition. It's similar to the thermal decomposition of group 2 carbonate or group 2 nitrate, as you will have encountered in your AS group 2 chemistry and also your O-level and IGCSE level chemistry previously. The last part of this question is identify another compound containing calcium ions. Basically, you must have calcium 2 plus. Also give CO2 and CO2 and calcium oxide, which is Ca2 plus O2 minus. So meaning the formula is going to be CaO. When heated, so I just talked about thermal decomposition of group 2 compounds. You can imagine that calcium carbonate is going to be one of the source. So when you heat this, you're going to get calcium oxide plus CO2. The answer you're looking for is obviously calcium carbonate. They say identify, so you can also give the name, but personally I like to give formula because it's direct and you should know how to write formula. From the name, you should be able to get the name from the formula. If they say name another compound, this is what you need to write, but they say identify another compound, so it could be these or these. This equation is not required, obviously. You will realize that when I do these kind of tutorials, I like to scribble around, but obviously the answer is just 1 mark asking for these rather than asking for the equation. But you never know when they could ask you for the equations because these are all part of your AS level chemistry. So that's the end of that 10 marks first question. question 2, so we have, question 2, we have this dot and cross diagram, and they are asking us in terms of similarity and difference, the atoms in the carbon monoxide are bonded together compared to the atoms in the nitrogen molecule. When you have nitrogen molecule, you have cross, 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 dot, 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 because nitrogen uses 3 out of the 5 outer shell electrons for forming covalent bond. You're going to get nitrogen like that. So you're going to get triple covalent bond. This is what I will scribble on the side as part of my working, as part of my thinking out loud process, because you're allowed to scribble things on the side. They are only marking whatever you do on the answer lines, so do not be hesitant to write out some stuff. CO is carbon monoxide, and that is exactly what they are showing you in the diagram. So essentially, the cross refer to the carbon electron. So you have cross dot, cross dot. So these are normal covalent bond, but the carbon has used up all the 4 outer shell electrons. So the oxygen uses 2 more electrons for forming dative covalent bond. This is a dative covalent bond because the oxygen is the one that provides both the electrons used in the covalent bond. Oxygen with the crosses, with the dots, it's got 2, 4, and 6. Carbon with the crosses, 2 and 4, because it's a group 14 with 4 outer shell electrons. So what is similar and what is different? You can hopefully see that similarity, both will have triple covalent bond. Both N2 and CO have triple meaning 3 times covalent bond. Well, bonds, because it's plural. And in terms of the difference is that how do I say this? These are normal covalent bonds. N2 has 3 normal covalent bonds, meaning to say 1 electron from each of the atoms, but CO has 1 out of the 3. 1 out of the 3 has 1 dative covalent bond, has 1 dative covalent. If you don't like the term dative covalent, it's also stated in your syllabus. There's a specification that is also known as coordinate bond, that is from the oxygen to the carbon. That is this pair of electrons there. There's this arrow that I'm showing from the donor to the acceptor. They say similarity and differences. Part 2, so question 2A, part 2, we got to use these electronegativity values. I have a feeling that this particular question, they give you this idea on electronegativity, is actually trying to angle you towards, in fact, it's trying to prepare for the new syllabus that's going to be assessed from 2022 onwards, where electronegativity values are expected to be a huge part in deciding the type of bonding for the new syllabus that's kicking in next year. I think it's just a trial of the, trying to see how the students will perform. So what we have here is use the electronegativity values, which of course we are given, carbon, nitrogen, oxygen. These are electronegativity. I've abbreviated it as EN, 2.5, 3.0, and 3.5. To complete the table below, the number of electrons, so you have number of electrons per molecule. We look at the total number of, what am I talking about? Number of protons. All right, that's what I'm looking for. We look at the total number of protons, first of all, because the number of protons would tell us the number of electrons, because N2, for example, has got 7 proton on each nitrogen, but there are 2 nitrogen atoms, so 7 times 2, which is 14 protons. But the molecule has no charge because the number of electrons equal to the number of protons, total number of protons. 6 carbon protons, 6 protons in carbon atom, 8 protons in oxygen atom. So you have 14 protons altogether. 14 protons altogether would also mean, again, 14 electrons altogether, because number of electrons equal to number of protons, because molecule has no charge. The compound literally has no charge. Now, how about the type of intermolecular forces? So, intermolecular forces. N2, the 2 atoms have the same electronegativity, 3.0 and 3.0. So, this is non-polar, because the N2 is actually non-polar, that means we only have van der Waals forces of attraction, or you can call this induced dipoles or temporary dipoles. But the CO, on the other hand, is polar because carbon and oxygen have different electronegativity. So not only you have van der Waals, but you also have permanent dipole because you are polar molecule, so permanent dipoles. Okay, so use the electronegativity and relevant details to complete the table. So that's all good there. Part B, so question 1, part B. Are we still on question 1? Yes, we are still on question 1. They're saying that nitrogen, N2 is less reactive because, well, less reactive than CO. Remember the CO has got the dative covalent bond like that, and they said it's because of the very strong triple bond. It's very strong. Oh well, now they're asking why is it more reactive. Well, you see this electron is actually donating from the oxygen to the carbon, contrary to belief that, oxygen being more electronegative, but it is dative covalent bonding to the carbon. You will see in A2 transition metal complexes that it is actually these electrons on the carbon that is actually forming bond to the ion center, ion 2 or ion 3, and that is what makes carbon monoxide very, very toxic because they are polar. They are slightly delta negative on the carbon, like I said, contrary to the electronegativity values, but these are proven by crystal structure data and also other evidence that suggests that it's the carbon that actually form dative covalent bond to the ion center there. So why is it more reactive? Well, CO molecule is polar. When it is polar, there is permanent dipole. When there is permanent dipole, it's going to be either attacked by something, because then it will be delta minus on the carbon, delta plus on the oxygen, so they can be attacked by something electron rich, or they can in this case form dative covalent bond to the electron deficient metal center. So there's permanent dipole, whereas N2 molecule is non-polar. And that's the very reason for the non-reactivity of nitrogen molecule in addition to the nitrogen-nitrogen triple bond strength. As a matter of fact, they are saying that the C triple bond O is actually stronger than this bond, but it's more reactive as a result of its bond polarity, in fact molecular polarity overall. Question 1, part C, we have ideal gas behavior. So it is most ideal when they just want us to state mean you don't need to explain. So this is most ideal when under low pressure, because when you don't have a lot of pressure, that means the gaseous molecules are further apart from each other, and therefore they are not attracted to each other, so they have very negligible intermolecular force because they're so far apart from each other. The other one is going to be high temperature, and this is related to what I just explained. At high temperature, your molecules have a lot of energy to move further apart from each other, and therefore negligible intermolecular forces between each other. Number 2 is about why the nitrogen gas behave more like an ideal gas. So the temperature and the pressure is not to be explained here because it's the same condition for N2 versus CO. You cannot talk about N2 having the different number of electrons than CO because that was just what you had done. They both have the same total number of electrons in the molecule, which is not 28, it's actually 14. It's the molecular mass that is 28 and 28. So be careful about the total number of electrons. So it's got to be the idea that N2 only has weak van der Waals forces of attraction between the molecules. As opposed to CO, which has the slightly stronger permanent dipole So that means the intermolecular forces between the molecules is going to be less negligible between CO molecules compared to N2. Therefore, the N2 is going to be have less ideally. However, they are asking us to explain that for 2 marks. So I've mentioned N2 has weak van der Waals forces attraction as opposed to CO, which has the slightly stronger permanent dipoles. I don't think they will give me my 2 marks. I need to be careful about the 2 marks. Why are they giving us 2 marks? I have compared them. I've talked about this is stronger. The permanent dipole is stronger than van der Waals. What else can I say? I should probably mention, I should really relate it to get the 2 marks, to relate it to the negligible intermolecular forces. Therefore, the intermolecular forces are negligible, are more negligible in N2 compared to CO2. In CO. Negligible in N2 than CO. Therefore, N2 is more ideal. In a way that is trying to relate these intermolecular forces, the strength of them, with the negligibility of the intermolecular forces, which is basically the assumption, one of the biggest and most important assumption for ideal gases. Question 1, part D, is the ideal gas calculation question, and that is actually the last 3 marks for this entire question. So we assume nitrogen behave like ideal gas, so PV equal to nRT. N is the number of mole, and this is what I want to find. In the ideal gas equation, let me just clarify, this is pressure, but be careful, it's actually pressure of the gas, and this is in Pascal, or it can be Newton per meter squared. V there refers to the volume, and that is incorrect. It's volume of the gas in meter cube. N is the mole. Mole of what? Mole of the gas. R is the molar gas constant. If you look in the data booklet, the molar gas constant is 8.31 joule per Kelvin per mole. It's the energy required to raise the temperature for 1 mole of a gas by 1 Kelvin. 1 mole of a gas. Everything in there is to do with a gas. So it's the temperature of the gas in Kelvin. T is that temperature of the gas in Kelvin. Judging by all that, if you then do PV equal to nRT, make N the subject first because that is what you want to find. So I always advise students to, don't put in the numbers and waste your time. Rearrange for what you want first and then write on the side all the information you have. The pressure is 101 kilopascal. That is not what you want. You want it in Pascal. So convert it to Pascal by multiplying by 1000. Your V is given in cm cube, and this is one of the hardest one to do. So think about it. 1 cm is 10 to the minus 2 meter, because 1 cm you divide by 100, you get meter. Then you're going to cube both sides. This is a classic trick. I never remember the conversion factor. I just work it out from scratch because, I can and I will. So 1 cube is going to be 1. Cm cube is going to be cm cube. 10 to the minus 2 cube, because it's cube the whole thing, it's going to give me 10 to the minus 6 meter cube. So converting 100 cm cube to meter cube is multiplying by 10 to the 6 meter cube. I do not want to, manipulate or whatever. I just write down my value and time 10 to the minus 6. Later on, I can key in my calculator easily. R is at 0.31 joule per Kelvin per mole from the data booklet. T is given in 20.0 degrees Celsius, so there's 20.0 plus 273, that's going to be 293 Kelvin. Be careful, do this on your calculator and you will get 293 Kelvin. Let me just double check just to be sure. Yep, 293 Kelvin. Now we are ready to sub in everything in the correct units. So I don't even have to write it down because I've gotten this, I've gotten all these. So 101, 100, 101,000 times 100 times 10 to the minus 6. Divided by 8.31 divided by 293, I have gotten 4.148 times 10 to the power minus 3, and this unit is mole. They didn't tell us how many significant figure, but judging by the data given, 1, 2, and 3, the 8.31 come from the data booklet. This is 101, so I shall assume that what is appropriate seems to be 3 significant figure. So if I just round that up to 3 significant figure, that should be appropriate given the data in the question as well as what I have used for the rest of my calculations. So that's the end of that questions, and I think we are ready to move on to the next part of the question. Question 3 is about group 17 chemistry. So this is about the reaction of halide salts with corn sulfuric acid. So we know that there is a general trend. So if this is oxidizing power, as you have seen me doing this quite a lot of times, back when I still have my full tutorial videos all over the place, but oh well, let's not reminisce on those good old times. Yeah, we now have this kind of restructured format. Eventually in time I'll have enough to actually compile and start over with a restructured topical playlist as well. Okay, anyway, so we have chlorine being one of the most powerful oxidizing agents from chlorine, and then followed by bromine, and then followed by iodine. In reality, fluorine, which is above chlorine, will be an even stronger oxidizing agent, but your group 17 curriculum just say from chlorine to bromine to iodine. Where does corn sulfuric acid lies? Corn sulfuric acid will lie as an oxidizing agent somewhere in between that of chlorine and bromine. What I can say is I don't know the exact position. I'm not even sure if they're distributed in exact proportion like this, but what is important in inorganic chemistry, so this is inorganic chemistry about the periodic table, do not be concerned too much about number, but concern yourself more about trends, and that is more important than the actual number unless you're given actual numbers, which you are in A2 electrochemistry but not in AS. So we know that chlorine is a stronger oxidizing agent than corn sulfuric acid. So corn sulfuric acid cannot oxidize Cl minus to Cl2. So meaning to say, in this first question, they say write an equation to represent the reactions of sodium chloride, solid, with corn sulfuric acid, which is going to be aqueous. It's going to give you not a redox reaction because there cannot be any redox since corn sulfuric acid is a weaker oxidizing agent than that. So what's going to happen is the acid donates protons. So the acid give away the H+, and what you get then is NaHSO4, because this is the salt that you get. After the H2SO4 donates the proton, you're going to get HSO4 minus, and that's going to combine with the Na from the sodium chloride. And where does the H go? The H goes to the NaCl, and it combines with the Cl minus to give you HCl, which will come off as a steamy white film, because this reaction is pretty exothermic, so they will give you that as steamy white film, and steamy white film is going to be gaseous state, and the NaHSO4 is going to be aqueous because this was in water anyway. Sulfuric acid is a mixture of H2SO4 molecule dissolved in water. So if there's your acid that donates the protons, there needs to be something else that will accept the proton, so the Cl minus accepts the H+, and that is why this is an acid-base neutralization reaction. So you got something that will accept the H+, that is going to be your base. Base accepts protons, acid donates protons, and you get this thing here, sodium hydrogen sulfate, which is your salt. You don't get water in this case, you get this HCl produced as a steamy white film. So this is not your classic neutralization, so not your classic neutralization. In fact, you cannot call it neutralization because neutralization would mean neutral pH. But obviously, we are not producing something neutral. We cannot call this neutralization. Instead, I think you really must call it as an acid-base reaction. So this is an acid-base reaction where you have an acid that donates proton and a base that accepts protons. We would typically call it neutralization, but in these kind of reactions where we are producing something acidic, so we are not really producing neutral pH. So you don't want to always call acid-base reaction neutralization, so just call it acid-base reaction in this case. So there's A part 1 for that balance equation. They haven't asked for stat symbols. I've just written out stat symbols out of font. If you don't have stat symbols, I'm sure you will not lose the mark as well. As for A part 2 is about the type of reaction, so it's just an acid-base reaction there, or you could call it displacement, where the chloride where the H2SO4 displays HCl out of sodium chloride. There's another alternative to this reaction, to this equation actually. So some people will have written down NaCl plus H2SO4 giving you Na2SO4 plus HCl. So they have kicked out another H plus, and in doing so you will get another HCl. In doing so you have 2 NaCl. That is perfectly alright as well. So both of these are accepted. You can write either one. Both of them will have the same implication where the acid donates proton and the base accept protons. Okay. In the next part of this question, so this is question 3, part B, part 1. So going back to what we have said earlier, where we have this trend. So corn sulfuric acid is a stronger oxidizing agent than iodine. So it can oxidize iodide to iodine. So there will be a redox reaction. So they say you get steamy white film. What is the steamy white film in that reaction? That is just your hydrogen iodide. You can write down HI because they don't say name the compound. They just say identify the chemical. Or you can say the name, which is hydrogen iodide. Hydrogen iodide is a molecule. If I draw the outer shell, it's going to look like this, where iodine now has a fully filled outer shell by sharing 1 electron with hydrogen. This is your year 9 dot and cross diagram for hydrogen halide molecule, because this is not hydroiodic acid. This is not acid because you are not dissolving this in water. This is a covalent molecule that has got a low boiling point. That's why it comes out as a steamy white film. As a gas, which is a pure substance, HI dissolve in water to give you HI aqueous, which is a mixture. Be very careful there. On to the next part of this question, they said that you get a redox reaction as the reaction continues with corn sulfuric acid, including a dark gray solid. The dark gray solid is going to be iodine because, as I said earlier, iodide can be oxidized to iodine, as corn sulfuric acid is a stronger oxidizing agent than iodine. So the dark gray solid is going to be I2. They say identify the chemical again. I would not hesitate to write down the formula, but what will not be accepted is if you write down I, it will not be accepted because there's iodine atom, whereas is iodine existing as an element, it exists as a diatomic molecule as an element. They say one other product. They say the chemical responsible for the dark gray solid, there's only one, and then they don't say the other product, they say one other product. The other product can be for the sulfur, and there are many possibilities actually. One of them will be H2S. This is sulfur minus 2. One of them could be sulfur, which is sulfur 0. One of them could be sulfur dioxide, which is sulfur plus 4. All of these are possible products, and you could write a balanced chemical equation for each and every one of these being produced individually. Okay, so personally I usually go for the H2S to remind myself that the sulfur goes all the way to the minimum oxidation state, and in doing so it passes by the plus 4 from the plus 6, because when you started from sulfuric acid H2SO4, the molecule has no charge, therefore the molecule has 0 oxidation state. The hydrogen has a plus 1 oxidation state. Then you have sulfur, then you have 4 oxygen, 4 times minus 2. So sulfur there is going to be plus 6 because plus 8 to the other side, minus 2 to the other side. You're going to get sulfur plus 6 as your oxidation state at the very beginning. I don't want to duplicate that. I don't know why I did that. Sulfur plus 6 go through sulfur plus 4, sulfur 0, and all the way down to sulfur minus 2. This is hydrogen sulfide. It has a rotten egg smell. This is a yellow solid. This is a foul smelling gas. It's kind of toxicating, suffocating kind of smell for SO2. All right. Question 3, part C. Explain the differences in observation. So you will see the plural being used, differences in observations. So we got to try and relate color changes and stuff now. So you have NaI versus NaCl. Okay, so they want the differences. The similarity is that both of these will produce HI and this will produce HCl. Both of these are steamy white film as a result of the high exothermicity of this reaction that releases a lot of heat. So this is similarity. Question can change to similarity. Well, I don't know why I said that. Question can change to similarity rather than differences, but here they want the differences. So differences, and they give us 2 marks. So I should really mention about difference number 1 first. NaCl, so no further observations, no further changes or observations or reactions can be seen with NaCl, but we can see dark gray solid being formed, dark gray solid being formed with NaI. Okay, so this is the iodine solid, I2 solid, as mentioned before. So obviously, again, no further changes could be seen with the NaCl. What else could be seen in addition to the dark gray solid? So this is basically a continuation of the previous question where we outlined or we stated the exact product that we could get. This is a dark gray solid, but the other products that can give us this suffocating gas, they can give us a yellow solid, they can also give us a rotten egg smelling kind of gas. Okay, so the reaction with NaI also further produce or form a yellow solid, or you can say cannot be a yellow solid, I guess, yellow solid. So observation means you don't know the product yet, but of course you know this is sulfur solid. You can also say a suffocating gas, that is your SO2. Actually, you produce the SO2 first before the yellow solid, because that is your sulfur plus 4 oxidation state. You also produce a yellow solid, and also what's the other one? Rotten egg smelling, rotten egg smell, and also a gas that smells like rotten egg, and also a gas that smells like rotten egg. So rotten egg is pretty bad smell. So this is your H2S, which is your hydrogen sulfide gas. In addition to the dark gray solid, you could also potentially get iodine vapor. Also possible is purple vapor. The purple vapor comes from I2 solid going to I2 gas. This is sublimation, and that could happen given the amount of heat given out by this reaction. So I'm just stating all these observations which will not be seen with NaCl, which will just give the steamy white film, which of course you saw it and you observe it with the NaI case as well, but there are other follow-up observations that happened with the iodide. Last but not least, in this question number 3, part D, for this 1 mark, is asking you what happened when you have bromide plus the sulfuric acid. So what's going to happen here is you really must know the resulting product first. This is with excess consulfuric acid. We know that consulfuric acid can actually oxidize bromide to bromine, but what you might not know is it will stop at sulfur plus 4, which is SO2, all the way. With iodide, it goes all the way to sulfur minus 2 in H2S with the iodide. With bromide, it goes to sulfur plus 4 only. And there's a case study, so you will get Br2, you will get SO2, and you will get H2O. So let's try and balance this. This is bromine 0. This is bromine minus 1. This is not hydrogen. I was looking for sulfur. It's sulfur plus 6, as I've shown you earlier. I'm not going to show you again. So sulfuric acid, how to work out the oxidation number of the sulfur in sulfuric acid. It's sulfur plus 6. And in sulfur in SO2 is sulfur plus 4, because each oxygen is minus 2. So minus 2 times 2 is minus 4. So sulfur plus 2 times minus 2. I am off my game here, but anyway, sulfur is plus 4 here. So sulfur plus 6 to sulfur plus 4 is a decrease of 2. Br minus 1 to Br0 is an increase of 1. Changes in oxidation number must be balanced. So I have to multiply this thing by 2 in order to balance the changes in oxidation number. And what happened then is I've got 2 there, but I cannot change 2 here because this is 2 times minus 1. So I have 2 times Br minus 1 now. So 2 bromine and 2 bromine. And the H plus come from HBr. So if I have 2 Br minus, I have 2 H plus as well. And that equation is balanced just like that, because 2 HBr, so 2 hydrogen. No, it's not balanced yet. I need 4 hydrogen, so I will have 2 there. And does that make sense at all? 2 oxygen, 4 oxygen, 4 hydrogen, 2 there and 2 there. So this equation is balanced now. Don't forget your water as well. So that's the end of that in my question number 3. Question number 4. We have a classic is it disproportionation? No, it's not disproportionation. I was mistaken. I beg your pardon. Okay, so Br2 plus HCO2H giving you 2HBr plus CO2. So they're telling you the carbon there is plus 4. So this is how you write oxidation number. The oxidation number of carbon is plus 4 in CO2. The oxidation number of Br is minus 1 in HBr. Oxidation number of Br is 0 in Br2. And the carbon there is plus 2 as told by the question in this thing called methanoic acid. So oxidizing agent, explain your reasoning. Okay, so if I have to explain it, so I will explain it first rather than stating it first. Oxidizing agent is defined as a substance that oxidizes the other substance. So oxidizing agent oxidizes the other substance, and what happened to itself? Itself get reduced. If itself get reduced, means itself, therefore, itself decreases in oxidation number. So we are looking at something that decreases in oxidation number. So this make your life a lot easier now. Br0 go to minus 1 is a decrease of 1, or you can think about minus 1 minus 0 is minus 1, so it's a decrease of 1. Self-decreasing oxidation number from Br0 in Br2 to Br minus 1 in HBr. So therefore, Br2 is oxidizing agent. You could say it like that, or you could say the Br2 is oxidizing agent because Br2 oxidizes the carbon plus 2 to carbon plus 4. So Br2 oxidizes the methanoic acid, causes an increase in oxidation number from plus 2 in here to plus 4 in here. Therefore, this is the oxidizing agent since it oxidizes that. Both definition will be accepted, both explanation will be accepted. I just like to define the substance first and then think about what happened to itself. So in part B, suggest one change you will observe when bromine reacts with methanoic acid. So they say ignore. This is what they specifically say. They say ignore temperature change. So you cannot talk about increase in temperature, decrease in temperature. What is very obvious is halogen. Halogen is colored. So halogen is deeply colored. Now this thing is not halogen anymore. So it is not color. Okay, the organic compound is colorless, carbon dioxide is colorless. So what we can say is the reddish brown color of bromine, and that is not correct. This is aqueous bromine, not liquid bromine, so be very careful. When you have aqueous bromine, that means you don't have the reddish brown liquid because you have a solution which is a mixture of Br2 liquid dissolved in water. So it's not going to be the intense color of liquid bromine. Instead, what you will get is the orange yellow color. So the orange yellow color of aqueous bromine, because in the state symbol they purposely give you Br2 bracket aqueous, will fade, or it will turn lighter, or it will, when bromine reacts, right, they don't say when the reaction is finished, will fade, will turn lighter, will turn colorless. eventually when it finishes reacting, when there's no more Br2 left. So the color will get lighter and lighter until it turns colorless, if it is used up, until it turns colorless when all aqueous Br2 is consumed or is used up. Because if the aqueous Br2 is present in excess, then obviously you will see a color still at the end of the reaction. With this part C, I've decided to actually copy the graph from the paper itself. So if you give me a minute, I'll stop this recording and I'll copy the picture from elsewhere. So I'm back. I have copied this graph from somewhere. Let's just not say where I got it from. And yeah, because it says use the graph. So part 1 is say use the graph to calculate the average rate of reaction. So this graph is concentrations against time. So we know that rate of reaction is defined as the change in concentration or the change in amount of something over the change in time. So they want you to find the average rate during the first 600 seconds. During the first 600 seconds, so what I can do is use the graph to calculate the average rate of reaction. They just want the average. They are not talking about initial. So if they have say initial, then we have to draw a tangent at t equal to 0, but they will not be for the first 600 seconds. They want for the first 600 seconds, and there's another key term there, average. Okay, so they didn't use the term initial, they just said average. So altogether, from the very beginning, I have 100, and then at the end, I have 20. So my rate is going to be the change in the bromine volume. Be very careful, read the graph. This is a reading times 10 to the 5. So this is 100 minus 20. Actually, it's not 100 minus 20, it's 20 minus 100, but the change is 80 because from 100 to 20, there's a change of 80. And this is multiplied by 10 to the 5. Actually, that will be wrong. It cannot be 10 to the 5 because if you look at it, it's the whole thing times 10 to the 5. So it means the actual value is actually very, very small, and you have to multiply by 10 to the 5 to get it to this number. So the actual value must be something times 10 to the power minus 5. Then what happens is you multiply this value by 10 to the 5 to get you to 20, 40, 60, 80, and whatever. So the actual value, it's going to be times 10 to the minus 5. For example, if you have 20 times 10 to the minus 5 mole per dm cube, that is small. But then what you're seeing here is 20 because you multiply this thing by 10 to the 5 in order to give you this reading on the graph. So when you multiply by 10 to the 5, you're going to see 20 on your graph, which is what you're seeing, but the actual value is not times 10 to the 5, but it's actually times 10 to the minus 5. That's why the times 10 to the 5 is on top there. This is quite tricky, but it's ultimately it's just your math and your physics, I guess, so be very careful. I was nearly tricked there, so be very, very careful there. And I think I got tricked again, bugger. Alright, okay, so I just so fixated on that 20. I almost didn't realize that, you see there's 20. That is actually not 20. That N volume there, sorry, N concentration there is actually this 5 square. So there are 5 squares divided for 20. So there is 4, 8, and 12. So there is 12 actually, which means this cannot be 80. Oh, what a bummer. So this is 100 minus 12. And then that is over a period of 600 seconds. So, oh, I cannot imagine this. Anyway, so 88 on top times 10 to the power minus 5. And then divided by 600 seconds, I get 1.47 times 10 to the power minus 6 mole per dm cube per second. This is mole per dm cube divided by second, so it's mole per dm cube per second to 3 significant figure. Phew, okay, nearly got tricked there. Be very careful. This question can be tricky, especially when you are not being aware of these kind of things, or if you are a bit lucky like me, then you go back and check your question. Otherwise, then you could make a lot of mistakes by reading this 20. Whatever. Okay, let's move on. So this is question 3. No, this is question 4 already. This is question 4, C part 2. Question C, part 2 is at higher temperature. So what happened at higher temperature is the rate is faster. There is a very large increase in rate. So what I want to do is I want to be able to show the reaction finishing very quickly. I don't want that. I want to show the reaction finishes very quickly. Again, I don't want that. I want a curve that, shows like that. Okay, so the reaction finished a lot faster compared to the previous reaction because there's a much steeper graph. What I can do is I can move that a little bit there, I guess. Is that good enough? No, probably not good enough there. Let's see. Okay, so there's a better curve. Well, not really better, but I can label this. I can label this at 40 degrees Celsius, higher temperature. I will still get the exact same amount of Br2 at the end of the reaction. Once the reaction is used up, once the reaction finishes, no more Br2 get used up, but it get finished or it get consumed or it get finished using up much faster than at the lower temperature. That's why it's a steeper gradient, steeper curve there. I've labeled my graph, so let's see on to the next part. So C, part 3, the rate of reaction increases when the frequency of successful collisions between reactant particle increases. Why? Why temperature increase? More successful collisions. These come down to your Boltzmann distributions. You are not being asked to draw here, but I'll just very quickly sketch out because it's an important concept in order to explain this. So this is energy E, and I'll have activation energy of the reaction there. Only the proportion of molecules having enough energy, which is those area that I've shaded, those are the proportion of molecules having energy greater than EA. Those are the molecules that have enough energy to react. When you change temperature, you change energy distribution. You can shift the whole thing down there when you change temperature. So what happened then is you get an increase in the area under the graph. In addition to the pink area, you also have the green area at higher temperature. That means you have greater proportion of molecules having enough energy to react. And that is how you should explain your essay. So at higher temperature, they talk about frequency of successful collisions. So at higher temperature, there are more reacting particles having energy greater than or equal to EA. Therefore, proportion of effective collision increases. The effective collision in this context refer to successful collision. So your rate will increase as a result of that. Rate increases. Okay, but I think there's only one point. There's actually another point which I haven't talked about. I should really talk about speed as well. So at higher temperature, reacting particles or reacting molecules would gain more kinetic energy. Because temperature is actually a measure of kinetic energy, average kinetic energy of the particles. So they will gain more kinetic energy. They move faster. They collide more frequently. So that is essentially what they have mentioned there, but I'm just talking about explaining in terms of gaining energy there, and I talk about the change in the distribution of the Boltzmann curve in terms of more reacting particles having energy greater than EA, and both of these combined together should give you all the marks you need in order to explain why temperature increase, rate of reaction increases. On to the last part of this question 4. This is part D. This is just dot and cross, and very importantly, they just want you to show outer meaning valence electrons only. So they provided you with circles. I will not draw the circles, I think. Do I want to draw the circles? Okay, maybe I'll draw the circles just to be in line with the question. So I have the circle with the oxygen there. I have another circle with the hydrogen there. Okay, and then I have another circle with the oxygen there. All these circles are really making me dizzy. I personally don't like to draw dot and cross with a lot of these circles. So oxygen and hydrogen, if you think about it, this is carboxylic acid, so it's going to look like that. This is a display formula where we show line diagrams. Each line is one covalent bond. One covalent bond is 2 electrons being shared. All of these are normal covalent bond. None of them are special dative covalent bond. So, you know, it will just be a dot and a cross. So if I start by saying that, you know, carbon is going to be cross, then I'll have cross, cross, and I'll have dot, dot. Okay, so the oxygen is dot and dot. I still have 4 more on this oxygen. So the oxygen is dot, and I use triangle for the hydrogen. So triangle and cross, because there's one covalent bond there. And then I'll have a dot and cross there as well. So a dot and a cross. And I'll have 4 more dots on the oxygen. Okay, counting electrons, I have 6 dots to begin with. I share 2 more electrons. I have 1 triangle, and then I share 1 cross from the carbon, another cross from the carbon, and dot from the oxygen. So 6 dots altogether, 2, 4, and 6. Another triangle there because there's your OH single bond there, just for your final 2 marks like that. If I were not given the circle, I would personally just draw, you know, like that. It's a lot easier without the circles. I just don't very much care for the circles. So what it would look like is like that. Without the circles, then, you know, it's a lot easier without having to do all that thing. But since it's provided, that's the end of that 9-mark question for question 4 there. Question 5, this is about organic chemistry. So question 5 started out by talking about what is meant by hydrocarbon. This is an O-level or IGCSE level question. Hydrocarbon refer to compound containing or consisting of carbon and hydrogen atoms only. So carbon and hydrogen atoms only. Okay, you should have a list of definition that you can prepare for. Name the raw material that is used to produce naphtha. So naphtha comes from the fractional distillation of crude oil. So crude oil is what you put into the fractionating column. You vaporize it, you boil it, you vaporize it, and then the different fractions will be collected based on their different boiling point. Of course, the lower the boiling point, the lighter the substance is, and it will be collected at the top of the fraction, and the heavier one will be collected towards the bottom of the fractionating column. So part B, compound V is found in naphtha. V is C10H22. When you heat it at high pressure, you get equal mole of ethene. Ethene is C2H4. This is alkene with 2 carbon. You get propene, C3H6. And you also get W. W is a straight chain, so it's not branch or anything. It is also saturated. Saturated means no carbon-carbon double. In fact, it just means only single-single. Only carbon single bond. Saturated. Hydrocarbon saturated molecules, because it has to be hydrocarbon since I started from compound containing carbon and hydrogen only. And they talk about straight chain, so it is not hydrogen. It is not hydrogen gas, because hydrogen gas doesn't have any carbon at all. This is equal mole, because they say equal number of moles. So this is 10 carbon. 2 plus 3 is 5. So perhaps I can have 5 more carbon. And I have 6 plus 4, which is 10. 22 minus 10 is going to give me 12. C5H12 is going to be, well, C5H12 is going to be pentane. CnH2n. Alkane. Well, CnH2n plus 2 for your alkane, I beg your pardon. So what if we say there are 2 of these? If you have 2 of these and 2 of these, then you have 6 carbon, then you have 4 carbon, then you have 6 plus 4, which is already 10 carbon. And therefore, when you have 10 carbon from this 10 carbon, you can only get hydrogen. You cannot be a straight chain saturated when you're only hydrogen, which means 10 carbon is impossible from the combination of these 2 and 2, which means it must be 1 and 1, which is why I'm left with C5H12 because there's only 1 and 1 of these. Anything more than 2 is just impossible, given that you only have C10 to begin with. So they want you to name the process first of all. So name the process. This is called cracking. Cracking is when you shorten up the long chain hydrocarbon into short chain hydrocarbon, which are more in demand. You are heating it under high pressure. This is actually thermal cracking, but I think if you don't put down thermal, you can probably get the mark as well. It's just that there's another type of cracking called catalytic cracking, where you will use a catalyst like SiO2 or Al2O3 as your catalyst for your catalytic cracking. Now they say deduce the structure, which I already did. I said cannot be 2 more there because you'll just be left with no carbon. So C5H12 is a result of the balance of the number of carbon and the hydrogen from C10H22, knowing the formula of ethene and the formula of propene, and of course then deduce the structure. So I want C5H12. C5H12 is not the structure. You cannot see the structure from molecular formula, so therefore you have to draw. It's a straight chain alkane, so this is a 1 2 3 4 5 C5H12 with 3 hydrogen, 2 hydrogen, 2 hydrogen, 2 hydrogen, and 3 hydrogen. Or you can write CH3 CH2 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 CH3 just like that. Okay, if you want you can draw a display as well, but you know I'm never a big fan of display formula unless I'm specifically told to draw it. Question part C, propene is separated from the mixture and you heat it in the presence of a catalyst. So you got propene, which is 3-carbon alkene, and then you heat it in the air. You heat it in the air in the presence of a catalyst. So you use a catalyst, you heat it in air, so this is oxygen from the air. You get oxidation, products. So propene is oxidized to X, which contain 2 functional group. Okay, so effervescence is seen when Na2CO3 is added to X. So you get effervescence. Effervescence means a lot of bubbles with Na2CO3. I'll probably just copy paste this onto a new page so that I'll have a lot more space to work with. So what happened with effervescence with Na2CO3 means I have CO2 gas. Therefore, X has carboxylic acid. Carboxylic acid is your acidic group. It will react with carbonate to give you carbon dioxide, metal salt, as well as water. Responsible for these observations, well, I just mentioned it, so it's got to be carboxylic acid there. So this is your part 1, C part 1. This is carboxylic acid. And then how do you show that X contain a carbon-carbon double bond? They said that when you heat it with these, you also get another substance with a carbon-carbon double bond. I suspect that the carbon-carbon double bond remains, and there's another carboxylic acid, which actually give you this resulting positive test there. You don't know the other one, but you are told that you have carbon-carbon double bond in the question. So how do you test for carbon-carbon double bond? That's the question. And then include relevant observations for 2 marks. So use, or you can say add aqueous bromine, or they say bromine water. Okay, so the relevant observation is presence of carbon-carbon double bond will decolorize bromine water, or I can say decolorize aqueous Br2, which is aqueous bromine there. So what actually it means is it will turn from orange yellow because it's not reddish brown since it's not liquid bromine. So you can also say orange yellow color of Br2 aqueous. turns colorless in the presence of carbon-carbon double bond or your unsaturated compounds, because you can add across the carbon-carbon double bond there. Part D, so what do I have in part D? Part D, I have X reacts with another reagent to form Y. So if I think about X just now, X has a carboxylic acid and an alkene. I can probably be thinking about this thing here, carboxylic acid and alkene. So this is probably X there. So if this is X, then they react with another reagent to give you Y. So something else give you Y. Y is the polymer. And Y is this polymer where you have C and C, continue and continue. And you have H and H there. So they've given you skeletal formula. They have drawn it like this. Then this is CO2 minus and then plus. So I get CO2 minus and then plus. And I get a H there. So that is part of the polymeric chain. Again, I'll copy paste this onto the new page so I will not run out of space to work with. That's one of the worst things someone can find them under. So that's your repeat unit. The question is, what is the structural formula of monomer Y? Let's see. What is the structural formula of monomer Y? X reacts with another reagent to form Y. Okay. So you want your monomer that comes from monomer. Your monomer is going to be CC double bond H, meaning to say I just add the carbon-carbon double bond and then get a H and a H and a CO2 minus and a plus and a H. Question is, how can I get from there to there? What is the structural formula of monomer Y? So this is monomer Y. So I think I got my answer here. That is going to be your monomer Y. Okay, in that square bracket there, monomer Y, this is part D. Okay, the question is, how do you get from X to this one? Well, you just need to deprotonate. You just need to deprotonate the acidic protons. So what you could do is you could react it with NaOH, or you could react it with sodium metal. Sodium metal is probably too much of a reaction to react reactive metal with carboxylic acid. You might as well just use sodium hydroxide. Of course, you could also use sodium if you want to. It's just too reactive a metal to react with carboxylic acid. Anyway, that's not the important question here. The important question has already been done. Now you have polymer Z. Polymer Z is useful because it absorbs large amount of water. As you can imagine, it's got this ionic side chain which can absorb a large amount of water because you can dissolve in water. Combustion is not appropriate. You don't want to combust this because the process releases harmful gas. Some of these gas contribute to enhanced greenhouse gas. So which of the gas can contribute to enhanced greenhouse gas? The one that will give you the enhanced greenhouse gas is going to be the carbon dioxide. So they say identify a gas. I can just write down the formula and that is perfectly and entirely fine because they didn't ask for the name, they just asked for the identification. I could write the name, I could write the formula, whichever one you write, they should accept it because the question never specify for the name or the formula. Okay, identify another gas which could be produced during the combustion of pure Z. Okay, polymer Z was not Y there, polymer is the Z. What else could be produced when you burn this polymer apart from carbon dioxide? One of the biggest problem when burning polymer, as you can imagine, if you burn plastic, is they will start to burn with a black color coming out because they don't like to burn completely because they have very long chain. So to get carbon dioxide means you have complete combustion, but obviously then you could get incomplete combustion that can produce carbon monoxide. Okay, the carbon monoxide is going to be toxic to your hemoglobin of your red blood cells, so those are really bad for you. So number 2 there, what else could be produced as a product? Well, carbon monoxide could be produced as a product due to incomplete combustion. Consequence, so the gas is going to be carbon monoxide. Of course, you could write down the name or you could write down the formula. And then the consequence, as we know, the harmful effect is that CO has a toxic effect on the hemoglobin. If you don't like to smell hemoglobin, then you can just say it has a toxic effect on human being. Okay, so it's a silent killer, by the way. That's the end of that 10-mark question with a little bit environmental chemistry and polymer chemistry towards the end there. Question 6. Oh, this paper has gone long enough. Anyway, question 6a, you have propene, so 3-carbon alkene there, reacting with H2O to give you an alcohol. So you could get that alcohol, but you could also get this alcohol where you add the H on here, then the OH on there, or you could add the H there or the OH on there. This H2O has to be steamed because this will be a reaction done at 200 to 300 degrees Celsius. You also need concentrated phosphoric acid as your catalyst. Now between these two products, which are both formed in reality, when you form this one, you will get it from here, this intermediate. When you form this one, you will get it from this intermediate. The carbon with the positive charge is bonded to one other carbon. This is what you call a primary carbocation. For the other product, they get it from this carbocation. The carbon with the positive charge is bonded to 2 other carbons. This is your secondary carbocation. Your secondary carbocation is more stable as a result of having more electron donating groups by inductive effect. These are all stated in the syllabus under alkene chemistry as part of electrophilic addition. You can catch my A-level tutorial playlist, A-level concept tutorial playlist, where I talk more on this under electrophilic addition, part 1 and part 2. As a result of more stable carbocation intermediate, that means this thing is going to give me the major product, and this other product on the left is going to be the minor product as a result of the primary carbocation being less stable. So what type of reaction is this? The type of reaction is going to be addition. That is the simplest thing they are looking for here. They are not looking for the mechanism, so do not write electrophilic addition, because if you look at introductory organic chemistry, electrophilic addition is not a type of reaction, it's the name of the mechanism. Addition is the type of reaction here. Now they want the name of the catalyst. Name the catalyst. So I want it in words and not formula. Concentrated phosphoric, and it's got a 5 acid there because H3PO4, it has a phosphorus plus 5 oxidation state, which I'm sure you know how to do because the whole molecule is 0 charge, 0 oxidation state. So I have plus 1 times 3 because I have 3 hydrogen, and I got 1 phosphorus, I got 4 oxygen, each of which is minus 2 there. So phosphorus there is going to be plus 8 minus 3 plus 5 there. So that's why we write down phosphoric 5 acid. This Roman numeral is very important to indicate that it's a phosphorus plus 5 and not phosphorus plus 3. On the other hand, the conditions, as I said just now, H2O just doesn't cut it. It needs to be steamed because this is done at a temperature of around 200 to 300 degrees Celsius. So, you know, your H2O will no longer be a liquid water at that particular temperature. Part C, so they're looking at C3H6 and also C3H at all. Did I tell us where C3H8O, which is the alcohol? So we could be looking at this or this one. So this one is propane 1-ol, or we could be looking at propane 2-ol. Doesn't matter which one we look at. because this question is about sigma and the pi bond. Whereas we're looking at this alkene here. If I just draw the display formula, because it's a lot easier to count it like that, I guess. So one of the few instances that I like to draw display is when I need to count the number of bonds. So here I'm just going to draw for propane 1-ol. Actually, I can draw for propane 2-ol as well. Don't forget that in display formula, it means show every single bond, including the OH bond there. Okay, so start by counting the sigma bond. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 sigma, and there's 1 pi because you have a double bond there. 1 sigma plus 1 pi there. There is no pi bond here, so you just have 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 sigma and 0 pi there. Okay, you could do the same thing here. You're gonna get 8 sigma as well. 1, 2, 3, 4, 5, 6, 7. I was wrong. I was so wrong because I have drawn ethanol. I said they should be the same, but they are not the same because here this is correct for propane 2-ol. This is wrong for propane 1-ol. Oh, what a bummer. Anyway, so I was missing 1 carbon. So let's start counting again because there was a mistake just now. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 sigma and there's 0 pi. Let's start again for this propane 2-ol, which I said should be the same as propane 1-ol, and by right there should be 1, 2, 3. Hang on, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So irrespective of whether propane 1-ol, propane 2-ol, for this alcohol with this general formula C3H8O, it's gonna have 11 sigma and 0 pi. So you can of course complete your table. I don't know if I have enough space to move this up a little bit. I do, so I'll just move this up a little bit. Okay, I'll just draw a line across to show there's the partition there. All good there. So what I have then is C3H6 for the alkene, C3H8O for the alcohol, so sigma and pi. There is 0 pi in the C3H8O, there's 1 pi there. There is 8 sigma in the alkene there. 1, 2, 3, 4, 5, 6, 7, 8. And then there's 11 sigma in the resulting alcohol product there. Question 6, part D. So they say the reaction, okay, so this question is about the more stable carbocation and the less stable carbocation. I'd just like to bring attention back to what I said. These are the kind of things that you should expect when you see these kind of questions, partly because, these are the kind of things that examiners really like to ask. So I know about identifying the carbocation by drawing the 2 possible products. Sometimes I will get this by drawing the mechanism. I'm surprised that this exam paper hasn't asked you on mechanism, but here it is. It's asking you on mechanism actually via this carbocation, which they are trying to ask you to explain for 3 marks. In a way, they're asking you on mechanism, okay? So, but they don't ask you to draw the full mechanism here. If I show you like this, so it occurs in a 2-step. So first of all, it reacts with the catalyst and form that. So what happened is you could have the H added there, but you could also have the H added on the other carbon. So this is a secondary carbocation, whereas this is a primary carbocation. Focus on the carbon with a positive charge is bonded to 2 other carbons. The carbon with a positive charge here is bonded to 1 other carbon. Primary carbocation is less stable than secondary carbocation, which is less stable than tertiary carbocation, because here you have 2 electron donating groups. So 2 times electron donating groups, electron donating alkyl groups, and this is by inductive effect. This term, inductive effect, is as stated in the syllabus. Okay, so they say draw structures to identify more stable and less stable carbocation. They don't say display, they don't say skeletal, they don't say structural, so I can do whichever one I like. Okay, but for the sake of showing you, very clearly what is going on. I'll probably do display just to be a little bit clearer. So this is less stable carbocation. So this is the most stable one. So there is your secondary one. So there is C, C, and C. This is a plus. There is a H. There is a H, H, and H. And then there is a primary carbocation. So there's a H, there's a plus there. A carbocation has only 3 bond pair and 0 lone pair. Therefore, around there must be trigonoplanar carbon sp2 hybridization, trigonoplanar carbon sp2 hybridization. The rest of the carbon is sp3 tetrahedral 109 degree. The rest of the carbon there, tetrahedral carbon sp3 109 degree there. So the secondary carbocation intermediate is more stable than that, and they're asking you to explain it. I've already explained it. So the secondary carbocation has 2 electron donating groups effect by inductive effect, whereas here you only have 1. Okay, so by comparing that, I can put it into words. Explanation. Okay, so the secondary carbocation is more stable than the primary carbocation. Due to having more alkyl electron donating groups by inductive effect. As a result of it, you could stabilize the positive charge. So these are electron donating, and these are stabilizing the electron deficient carbon center. Compared to here, you only have 1 electron donating alkyl group to stabilize this electron deficient center. Okay, so that's enough for the explanation, and they want you to name the major product. So having a look at these, if you think about the resulting mechanism, so your H2O with the lone pair will attack the carbon there. Your H2O with the lone pair will attack the carbon there. So your resulting alcohol, which is going to be propan-2-ol versus propan-1-ol, as I have named them earlier. So I'll just copy down this thing, propan-1-ol versus propan-2-ol. This is going to be major because they come from the secondary carbocations. This is going to be minor propan-1-ol product because it comes from the less stable primary carbocation intermediate. So the major product, so question 6, part D, part 2, name. They want the name, they want the major, they want the organic. Okay, so be very careful, they want the name, so it's going to be propan-2-ol, having identified the most stable carbocation just now. On to the next part of the question, which is the last bit in this question. So you have 2 bromopropane. So this is 1, 2, and 3. 3 carbon alkanes, bromine at position 2. They can react to give you propene, and then HBr, and then H2O. Okay, I can see the HBr, but I can't quite see the H2O quite yet. But they're not asking us to balance this equation. I hope you can see that you go from halogenal alkane. So halogenal alkane, which I usually abbreviate as RX, to alkene. This is going to be elimination. This is elimination of HBr or HX, because opposite to elimination is going to be addition. This can electrophilically add onto the alkene to give you this halogenal alkane. So name this type of reaction. The type of reaction very clearly is elimination. As I said, one substance can give out more than one substance. Is the opposite of addition. So E part 2, describe the reagents and the conditions to favor. You want to favor elimination. So what you do is you use sodium hydroxide or potassium hydroxide. potassium hydroxide or sodium hydroxide, and your conditions are very, very important because you cannot use it in water. If you use it in water or aqueous condition, then you will get substitution of the Br with OH, which is called hydrolysis or nucleophilic substitution mechanism. So the condition has to be in ethanol, can never ever be in water if you want to favor elimination. And this has to be reflux, so reflux in ethanol. This is the solvent in which you contain the NaOH. If you use sodium hydroxide aqueous, so I'm talking about if you have like this, if you use aqueous NaOH and reflux, you are going to get like that. This is going to favor substitution. It's going to favor nucleophilic substitution, which is actually hydrolysis, because you are breaking the CBr bond in the presence of water. Aqueous NaOH means in water. If you do it in NaOH in ethanol or KOH in ethanol, you're going to favor elimination, so you can get like that. That is what the question want you to try and think about. Substitution versus elimination. Very, very popular concept. Okay, so that's the end of that 12-mark question, and in fact it's the end of this paper. This is paper 2, May, June 21, very recent paper at the time that I'm doing this particular one. So May, June 21, paper 2-1 for the 9701 chemistry. Okay, so if you enjoyed this tutorial, make sure you click the button on the bottom right to subscribe to the channel. Share the channel widely with all your friends, chat group, juniors, seniors, teachers, relatives, and many other people. Okay, and follow me. So do follow me at ptet.chemistry on Facebook, Instagram, and Twitter to get connected and to send in messages and questions. Thank you for watching, and I'll see you in the next tutorial video.